All right, let's talk a little bit about avgas versus autogas. Well, I think when I wrote this, my thought was more along the lines of legacy aircraft, you know, your Cessnas and your Continentals and Lycomings. There's an STC, supplement to the type certificate, that allows an aircraft to be run on car gas or MoGas, whatever you want to call it, same thing. And in essence, what it is the aircraft was certified to run on 8087, and because it's cheaper, people would then go fill up their 5-gallon cans and take them out the airport and run it. And so my thought process was more along that line, was when I wrote my notes. Like, well, is that a good idea or a bad idea? And I'm not a proponent of that by any means. Although I'm becoming more of one the more I look at the effects of lead on the engine and think about it from that standpoint. But with so many light sport aircraft just exploding in the last, 5-10 years, that we have to look at avgas versus autogas in a different light. Because if you're running a light sport, Rotax, and some of those engines, you're going to look at it from a different perspective. If I stand over there in the light sport category and go, well, I got a Rotax, autogas is the thing to have. When you're selecting 100 low lead, you're kind of making a mistake. But then when you come over here and you look at, well, I can't see my airplane because I have to run it on 100 low lead, but the 150 that I had, I feel that autogas is a mistake on that end. So it's just kind of weird how that goes, but you can make up your own mind. So in order to run your Cessnas, Beechcraft, Continentals, and Lycomings on car gas, you have to purchase an STC. And I don't think it's very much. I don't know, it's like $100 or some crazy thing. I don't know. And all you're going to get is a piece of paper and, in some cases, a little band that you can clamp around the oil filler neck that says STC and has the number on it, that you paid the money to the person to put car gas in your aircraft. And, of course, again, the only upside that I can think of is that you don't have the lead. That is the only upside. But the downside to that is that we have to look at a couple of things. So let me see. So for one, if you want to run your legacy aircraft on autogas, you need the STC, and it's only possible. So you need an STC, and only possible for aircraft with 8087 as the minimum octane. So what are the benefits? Well, no lead. So that would be reduced sludge. 2, no lead, no spark plug fouling, so no lead fouled plugs. And if you choose the right product, very clean intake ports. Oops. You take a look at a cylinder that's been run on 100 low lead, and the intake side, it's a little gummy and sticky, and it's got that blue dye all over it. You take a look at an aircraft that's been running Chevron or Shell gasoline. I don't know about the other ones, but I could always tell Shell or Chevron. It's cleaner than the day it came out of the factory. I mean, the ports are just polished and super clean. That whatever they're putting in their Tectron and stuff, that stuff works. I mean, it really cleans the intakes. So there's your positives. That would be so your cons. So car gas does not have the same. So car gas has lower quality control. Long time ago, Chevron accidentally leaked a little bit of Jet A into their 100 low lead here in Sacramento area during an air show. And everybody who filled up, because they take your N number when you purchase fuel, they got a new engine, courtesy of Chevron. Either got it boxed, shipped one to you from the factory, or you got yours overhauled. No questions asked, no parts returned, you just got an engine. Excuse me. So I hear stories about on the radio about, you know, people who are buying, oh, Circle K down over here, 20 people are reporting bad engines. Have you guys heard that stuff? I'm not really saying the Circle K over here. I'm just saying I've heard. And recently about, a group of people saying, hey, we got gas at this one station and, ruined our engines. You ruin your engine in your aircraft, you have no recourse if you're using auto gas. I don't think you're going to have much luck going to the Circle K and explain to them why they owe you $100,000 for your engine. So that's a huge risk. And considering I've actually seen it happen where fuel is contaminated, people got new engines, it's a possibility. Car gas contains alcohol and other things.
So the lower quality relates to not being able to be reimbursed?
They have different quality controls altogether.
Okay.
When they produce it, I don't know how tightly they have to constrain those octane ratings. Because with modern cars, if your octane rating is off, the NOx sensor is going to pick it up and protect the engine. Not going to do that with an airplane engine.
They also don't have the same level of quality control checks that aviation fuel does.
That's what I'm saying. Quality is lower quality control.
Okay.
Because I pump fuel every morning. We have to go through and inspect it every morning.
Okay, that's right. Yeah, at the pump,
Yep.
at the distributor. Yeah, you don't see them out there checking filters every day. In fact, you sometimes go to a pump. It's like, man, it barely runs because their filters are so damn clogged up. You're not getting anything out.
Yeah, so that's a risk of using car gas.
Yeah, yeah. Okay, contains alcohol and other chemicals. Not compatible with some of our rubbers and things that are in aircraft. Alcohol. What's the alcohol in the fuel for? Cheap. Didn't it collect the water? Yeah. Alcohol holds the water, and so that's not good. We want our water separated out of our fuel in aircraft because water and fuel can freeze. We don't want to freeze components. Right, so you have alcohol in there. That's not a good thing. Let's see, quality control. Higher volatility. Auto gas. Let's say auto gas. So we have higher volatility. What's that going to lead to? Not detonation. Vapor lock. Higher volatility, which also means a higher vapor pressure. Let's see. Oh, and this is a big one. Not as stable. Not as stable. And by that, I mean, auto gas doesn't last. It doesn't have a long shelf life. It has a much shorter shelf life. You talk with people with boats who want to park your boat for the season. They have to put fuel stabilizer and stuff in it. We don't have to do that with aviation fuel. Stuff lasts a long, long time. At the class this week, we got on this subject, which is funny since here it is. And he was saying that the instructor, it's a friend of his that lived down the street, went through this experiment. So he took a test tube, and every month he would go down to the gas station and he would fill up his test tube and put a rubber stopper in it and put it in the rack. So there's January, all right, February, March, April, May, June. When he got down to December, January was nothing but a bunch of varnish and tar in there. It had evaporated through the cork stopper. But aviation fuel won't do that. So, take your pick. Like I said, Rotax is pretty adamant about they were designed for car gas. Please run it on car gas. If you're going to use aviation 100 low lead, then your maintenance you need to do a lot more maintenance. Anyway, make up your mind. Because as a mechanic, people ask you, hey, what do you think? Should I run car gas? Or, that's what I tell them. Well, it's not as, quality controls aren't as good. Tell them about the Chevron thing. That's enough for me. So, all right. I call this chemistry, but it's not really chemistry. Is it? Yeah, not really. But this is the good stuff here. So, we'll call it chemistry. But I'm not getting into too much in chemistry. All right, so fuel is a hydrocarbon. So gasoline, I should say. Gasoline, let's call it fuel for now. Fuel is a hydrocarbon. That's hydrogen and carbon.
This is half gas, right?
Gas, fuel. Gasoline.
Gasoline.
All right, so each molecule is 8 carbon atoms and 18 hydrogen atoms. And as we've already talked about, gas needs to be in a gaseous state. Means it can't be a liquid when we burn it. We want it as a gas. It needs oxygen to burn. If you remove all the oxygen, it will not burn. So if we take a look at air, or air about us, by weight, air is by weight, mostly nitrogen. 75.3% nitrogen. 23.15% oxygen. And 1.55% other. So that's by weight. By volume, instead of weighing it, take a cube or sphere or whatever you got, a closed container, and it's going to look more like, which I like these numbers better because they're easy to remember, 78% nitrogen, 21% oxygen, and 1% other. Cow farts and whatnot. So we got to mix this air enough to get the oxygen that we need to burn the fuel, to get the power. So let's talk about mixtures. Fuel mixtures. All right, this is the heart of stuff right now. So starting now, you gotta pay attention. In fact, if you wrote this. This section is possibly the most critical section. Failure to grasp this concept will make passing the course very difficult, if not impossible. So make sure that you stop me and ask questions if I say something that doesn't make sense to you, and we'll see where we go with that. All right. So for fuels to burn, it must be mixed with the correct amount of oxygen. For fuel to burn, it must be mixed with the correct amount of oxygen. So if we had a bucket of fuel right out here in the open and we light it on fire, we don't really have to worry about mixing the oxygen. It's just going to take the oxygen around it and there it goes. But we're not. We're going to put it inside of a closed container, cylinder, close up all the ports, and then burn it. Well, if you didn't get it right, you can't go out and get more oxygen. You can't go out and get more fuel, so what goes in there has to be correct. And that's the job of the carburetor. So we want to understand what it is the carburetor is trying to do. So, all right. So there are basically 3 classifications of mixtures. There are basically 3 classifications of mixtures. And they are simple. There is the rich burn. The rich has an excessive amount of fuel, not enough oxygen. So to fix it, you could either take away some of the fuel or add more air. Well, in a carburetor, the air is pretty much just going in by the butterfly valve, the throttle plate. So it's much easier to control the fuel. Rich, neither rich nor lean. Neither rich, I should say nor lean. It's right in the sweet spot. So it has the correct amount of oxygen. That's correct. Amount of oxygen. And 3 would be lean. So running through the whole gamut. You got rich all the way to lean. So lean, what do you think that's going to be?
Excessive.
Yep, has too much or excessive air or not enough fuel. All right, and I talked about this just a little bit, but now we'll talk more. Stoichiometric. 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 It is the chemically correct blend of fuel and air. So chemically correct blend of fuel and air. It is purely theoretical. Now, the reason why I'm stressing this chemically correct, I shouldn't say it's purely theoretical. It's not. It's science. It's chemistry. But so theoretical wouldn't be the right word, but I'm going to throw that anyway. And the reason why I say that is because inside of our closed cylinder, we want the exact right amount of fuel with the exact right amount of air. So you would think that we're closing it all up. Why would it not be the chemically correct mixture that they're going to give us here? I'll give you in a second, 15-1. Why is it not that? Well, it's simple. Because in order to get this stoichiometric perfect chemical burn, you must mix everything up and have it all dispersed evenly. That doesn't happen inside of a cylinder. We have air coming in and fuel coming in from an open valve, and they're going to come in and not be perfectly mixed with the air. We may have some spots that are a little bit richer, some spots a little bit leaner. We'll have spots in the cylinder where this side of the cylinder is actually a little richer than this side of the cylinder. So we have this problem going on where it's not because of the design of the intake and the cylinder and where the spark plugs go and how it's all working out, plus the fact that it's happening so quickly that things just don't mix perfectly. So we will discover that some engines need a little bit more fuel that would be stoichiometric to actually run properly, right? Just because of the unevenness of the mixture coming in. So when we talk about the perfect sweet spot in the engine, it's not stoichiometric. We call it best power.
It sounds like this, like how you mentioned scientists. It sounds like they only can get that in like in a lab controlled environment type setting, as far as.
You know, I'm sure you could actually get it very simply on your own if you could measure out the 15 parts air to 1 part fuel, put it in a closed container, swirl it up really good, give it a few seconds and the right temperatures and ignite it. I bet they'd be easy to do. It's just think about how fast it's happening. I mean, it's way faster than that.
So many variables.
And the way it's coming in and swirling. So yeah, in fact, that's one of the reasons why the small Continental, the C85, has staggered ignition. One spark plug goes a few degrees before the other because they want to start, because of the unevenness of the mixture, it burns at a different speed to the point where they've actually lighted off on one end of the cylinder at a different time than the other, so they both meet in the middle. It's like this is burning so fast here, this one's burning too slow.
Yeah, closer to Stoichio. Yeah.
So one is best power, one is not. The big bore Continentals, they have one spark plug going like this and one going like that. Same reason, you know, they're trying to, because they want to light it going that way, and you know, so it just, it's not what really happens in the engine. So I know I listen to some podcasts and they talk about that. Well, they're not stoichiometric. It's not stoichiometric when the engine is running perfectly. It just doesn't happen that way because of the way the engine is running. So not that makes a big deal, but it just is. So in this particular case then, all the fuel is burned. All the fuel is burned. And no extra oxygen, right? This is a ratio of 15 to 1. And thankfully, it's 15 parts air to 1 part fuel. If it was the other way around, we would be in big trouble. It would be very expensive to operate an internal combustion engine if I needed 15 times more fuel. So 15 parts air to 1 part fuel. Ratios are also sometimes written in the form of decimals. I do not prefer to do it in decimals. Maybe your brain works a little better that way. But 1 divided by 15 is 0.067. So you will often see these ratios given as a decimal. I think, to me, it's more visually appealing to look at it as a ratio. And it's always going to be to 1. Huh? It is by weight, which is why I started with the method in why I gave you this here by weight, because it's actually by weight, but we really learn it more by volume here. But anyway, this is 15 to 1. I can put that by weight.
Phil kind of talked about it.
Good. Well, actually, my next point actually got rid of that. 15 pounds of oxygen to 1 pound of fuel. That is 15 pounds of air to 1 pound of fuel. Let's see. I don't need to write this. 1 pound of 1 pound of air is about 13 cubic feet. So that would be 6.7 pounds of gas to 100 pounds of air. A little over 1 gallon of gas to 100 gallons of air. So that would be a room that's 10 by 10 by 12. So. It's about 10. About 10 right over here. So 10 by 10 by... A little taller than that, because that's only 9-foot ceiling. So 9, 10 by 12, another 3 feet up. That's how much air we need for a gallon of gas. Ah, got my pictures. Red was the 8087. Green was 100, 130, but now if you see green, what is it?
A mixture of 50.
Yeah, it's UL, mixture of UL. It might be UL, might be a mixture of UL, and of course blue is 100 low lead. That looks a little purplish. Oh yeah, I pulled this, forgot, got this off Gamy's website. Brand new slide. That to me is,
I don't know if you call that animal.
okay, if you didn't label this, you said, Kevin, what is this? I would say 100 low lead, Zyglow, and something else. Green Gatorade. Yeah. No, if you need to drink more water. Okay. Maybe I'll just talk for a little bit here and get my slides. Let's see.
How would you know that you're at your best power?
We are so going to talk about that.
Okay.
I'm so glad you asked that question. I'm just sitting here thinking, how do I want to best introduce this and make sure I don't lose anybody? So we'll write these two things down. Let's talk about a rich mixture, because it has a characteristic. A rich mixture. It's, say, I hate to use the word little, but because it's more fuel, but we always talk about fuel as being the one, therefore it's the air that fluctuates. So as little as 8 parts air to 1 part fuel. So 8 to 1. That's by weight, of course, can still burn. So that's so that'd be 8 to 1 or 0.125. This is important here. A rich mixture burns slower than the correct mixture. Now I'm using the word correct, not stoichiometric. Because again, stoichiometric does not apply to what is happening in the cylinder. And in a little while, I'm going to change that word to best power, and you'll understand that. As opposed to a lean mixture. By the way, some books vary a little bit on this. I want to keep it these numbers because I think it's the easiest to remember. As much as 18 parts air. So I have 8 and 18. I can remember those numbers. Air to 1 part fuel. So that's 18 to 1 or 0.055. Okay, a rich mixture burns a little slower than the correct mixture. A lean mixture burns way slower. So at the correct setting, we have the fastest burn. We go a little bit richer, it is going to burn slower. We go leaner, we can go a lot slower. Yeah, good. This is the slide I want. All right, but you have to be careful because you can't just say lean burns slower, because if this is the best power and we go a little bit richer or a little bit leaner, well, they're both on the same time, right? So you can't just say leaner burns slower. It's that a rich mixture will only get so slow and then completely die. The engine dies after this. By the way, this right here would be what ratio?
8 to 1.
Right, 8-1. A lean mixture, because we'll say it dies off right about there, a lean mixture runs all the way to right there, and that point is where? What's my ratio? 18-1. That's really slow. So we can really slow down that burn. And also you can see that it starts slowing down a lot faster. And goes much slower.
Excuse me, is it curve RPMs?
Time.
Time. Okay.
Yeah, this is time. And this is rich lean down here.
Okay.
Flame propagation rate. That means how fast the flame front moves. Now, once you understand something like this, or at least kind of start paying attention to it, it opens up a whole lot of possibilities of things you can start to understand. Why things do what they do. Because it's going to get a little bit complicated, but it doesn't have to be. It's just you really have to stop and think about, okay, wait a minute, that's because the flame is moving slower. Time is happening.
So yeah, the more air, the slower the flame.
The burn.
Right. Slow. Okay.
Now the engine is still running at the same RPM. So if I'm running at 2200 RPM, that engine isn't changing its revolutions per minute. Everything is happening at the same time. But now suddenly, if I can take the flame and make it last longer or shorter, I start affecting things. And as pilots, we can see those things and manipulate them. We have to understand what those things are. Then when we understand what's happening, then we start to be able to talk to the engine and understand what it's trying to tell us. We can't talk to it, it talks to us. It tells us what's happening and why it's happening. And is that good or is it bad? So, all right. What else I got here? Oh, yeah. Oops. I'll discard. Didn't mean to do that, but all right. All right, lean mixture. 18-1. And let me see. Lean mixtures burn very slow. Lean mixtures burn very slow. Or have the capability to burn very slow. Because like I said, just a little bit lean isn't really that slow. It's the same as a little bit rich. A lot lean burns a lot slower than a lot lean. There is a Q&A that says excessively lean mixtures can burn so slow that the fuel is... no, that's not the question. The question is something about which mixture I think can cause a backfire. You guys probably haven't gotten into them yet since you didn't even do the waivers. There is a question about which mixture can cause a backfire. And not all of the FA questions are the greatest, if you haven't figured that out yet. So I think it's something like that. We'll just write that. Which mixture can cause a backfire? Backfire is a what? Burp or fart? Burp. Yeah, coming out. It's coming out the intake. It's going backwards. So the answer is lean. I think the answer is a lean mixture.
Are they taking that as a excessive?
Excessively lean, not just a little bit. And the reason why is because intake, compression, power, exhaust, intake. Their theory is, and I don't know about this, excessively lean mixtures can burn so slow that the fuel is still burning when the intake valve opens. That is the answer that they're given. So we got the fuel burning all the way through the power stroke.
Yeah.
Then the exhaust valve opens, and it pushes out the thing, and then
And it's
still burning.
by that time.
I don't buy that. I just, that seems a little,
Doesn't make sense.
little like, I don't know. It's okay then. But anyway, that's a question. Let me see. I had read somewhere, because I'm like, what? It said excessively lean mixtures burn so slow that the fuel is still burning when the intake valve opens. This causes the fuel air mix in the induction to burn and causes a backfire. I wrote not likely, but known to happen on some radials because of the way they are. But anyway, that's the answer.
Do you have a theory of your own as far as why some engines backfire?
Well, you're lighting off the fuel and the air in the induction system. So what can cause that are a couple of things. One, you can get that when you have a hot spot or something when the intake valve opens. If you do have it, or mistimed or something, that will light it off.
Okay.
Could be, yeah.
Apply that to an automotive application. If you had a high overlap, where that
Really high overlap, yes.
which would be good for a high RPM engine
Yes.
operation, but you're just starting out and you stop it, you lean it out, you'll get a backfire up to the carburetor.
Yeah,
That's,
yeah.
I think it's proportional to your overlap.
yeah. And I forget, we don't have overlap in flat engines here. They move too slow. So, but I think radials have pretty good ones. So there you go. So it's true, but not as applicable to our engines as it should be. Okay, got that. Let me just reiterate this point. So burn speeds. Burn speeds, let me see. Both rich and lean burn slower. So both rich and lean burn slower than best power. But a lean mixture has the ability to burn the slowest. And I'll just throw this in here just to remember. So we have, let's stick with the chart here. Lean on the left. Dang it. So we have lean, we have rich, and in the middle we had stoichiometric, in a perfect world, but not, so it's really more best power. Which in a perfect world, that would just be stoichiometric, but because of mixing, we don't. So lean is going to go as much as 18 parts air to 1 part fuel. best power is, oh, it's probably really more about 12 to 1. And then rich will go all the way to 8 to 1. What happens if we have 7 to 1? The engine going to run?
No.
In theory, no.
Will
Huh?
it actually run or?
No. Nope, stops. Doesn't have enough air. You've snuffed it out.
Mm-hmm.
In the Navy, I don't want to bore you with those stories. But anyway, we called it an upper explosive limit for firefighting and gas-free stuff. It meant that it's so much explosive material, so much fuel in it, because we had enclosed, just like a wing tank, but ship is full of voids. And you go in there and you test the quality of the air, and if it had fuel at one point in it, you'd say, wow, the fumes in here are so bad that you could bring a match in here and you wouldn't be able to light it because there's no air. Right? Upper explosive limit. But you open up that door for a few seconds and it's going to light off up there because air is starting to come in, and now you've gone from that too rich to burn into, oh yeah, we're getting air, it's going to burn now. You try and light a match over there next to that open port, it's going to explode the whole thing. Then we go all the way through down to 18 to 1, which you call the lower explosive limit, which meant it's never going to burn because you have so much air and so little fumes to burn that it's just not a problem. So, all right, so a little bit leaner, a little bit burn at the same, a little bit leaner and a little bit richer, pretty much burn at the same speed, right, as on the chart showed. So a little bit leaner, or a little bit richer, burn at the same speed. And I'm not going to write this, even though I put it in my notes because it's being redundant, but a lean has the ability to go much, much slower.
Professor, or Kevin, excuse me, can you write, show us on that graph where the little bit leaner and the little bit richer is?
Yep. I like this. Okay, best power. In a perfect world, that is what?
15 to 1, 12,
15 to 1, and also called stoichiometric. But in an engine, it's probably closer to 12 to 1. Depends on the engine. Okay, you can't just say 12 to 1. It really depends on the engine. All right, and so really this should peak right here. This should be the peak. So just a little bit richer right there, and just a little bit leaner right there. Right, they're on the same level, and if they're on the same level, that means their time is exactly the same. Just like I could find, I had a straight edge to put up on there. I don't have one.
Freehand.
There you go. Yeah, just like those two spots are the exact same time,
Okay.
right? And these two spots are the exact same amount of time. So on and so forth until we get to right here. Those are the same amount of time. That's dead, and now we can just keep going slower and slower and slower. But on that side, the engine would have died.
Okay.
All right.
And that's the same thing as if it gets too much air, then it's not going to work either.
Yep. Once we get over here, too much air, it's dead. At this point, it's dead. 18 to 1, dead. Anything after that, 8 to 1. Anything after that's more than 8 to 1. All right. So one of the points to this, and there are going to be many, is that when we talk about engines and where the piston is on its stroke, the timing of it means something, because are we pushing on the piston when it is top dead center? That'd be bad because they have a tendency to kick back. Just a little bit past, more past, or we, way down here before we're pushing on the piston. So that has to do with the peak pressure point. And the peak pressure point, I don't know, maybe that drawing has something to do with peak pressure point. I'm not sure what they were trying to show, but I know what I'm trying to talk about. The peak pressure point has a lot to do with detonation. So burn speed is important. I should get back to my 3. Burn speed is important due to where the peak pressure point happens. That's the PPP. Well, obviously, the PPP, I should just put P cubed, should happen after top dead center. So remember, we're going to fire off these spark plugs 25, 30 degrees before top dead center. If we get our peak pressure point happening while the piston's on its way up, that's bad news. It's got to come up to top dead center and start its way down before we start pushing on the crankshaft. You push on the crankshaft when it's on its way up, you got problems. Right?
Yeah. So,
Because that's where we lit it off. We lit it off while it's coming up.
right.
And we need the pressure to start building and now push.
And we want the peak to happen on the
Downside.
Right. Okay.
Yep. So you start messing with the time, and then that has a problem. But of course, ideally, you still want your peak power, right? We're not trying to kill power off to move it on this side of things. We still want peak power. Oh, all right. But I'll get more into that. So let me see. Obviously, it should happen there. Let's see. I don't want to say something confusing. Well, I put at high power settings, a rich mixture will move the power PPP to after top dead center, but of course so will the lean. So I don't want to write that. I'm going to write this though because I like this point. Where the PPP happens will have an effect on cylinder pressure, detonation, and temps. All right, good place for a break.
Right.